Alright, we've got a rock that breaks loose from the top of a tall cliff, and we want to know what its average speed is during the first 2 seconds of fall. So find the speed of the rock when t equals 2. So a couple of things that are going on here. Number one, we've got a rock falling off a cliff, so I'm just going to draw a picture here. This is going to be very generic, and here's my rock right here, and we're going to give it a push. So we're back here like this. We're going to push the rock off, and it's going to fall over the cliff. And it's going to go down, down, down. Well, this is at t equals 0. We're here. And t equals 2 is down here, so we're going to have time. The other thing that we're looking at is height. So if I start here and stop here, this would be like height. We'll put that in red. Okay, height. So what we're wanting to do is determine what's the speed of the rock after it's fallen for 2 seconds. So go back to physics class, and you'll recall that when you're looking at gravity on Earth, you have a kind of a generic equation of 16t squared. Now, this would be negative 16t squared. We're falling, but we just want to know how far we went. We're not necessarily concerned with, like exactly how high or whatever right now. We just need a total distance, okay, like an absolute value. And so when you do that, what we need is change in y divided by change in time. This will give you an average. In other words, if you can take where you stop minus where you start and divide that by the time that you stop minus the time that you start, you're going to get an average. So how does this look for our particular problem? Well, our function is t squared. So we need to know our stop time is when t equals 2. Our start time is when t equals 0. Our time on the bottom, we stop at 2, we start at 0. And so when we set this bad boy up, what we're going to end up with is 16 times 2 squared minus 16 times 0. On the bottom, we're going to have 2 seconds minus 0 seconds. So 16 times 4 minus 0 over 2. Okay? And this is going to equal 32 feet. That's how far we fell on the top, divided by seconds, which is how long we lasted on the bottom. So this guy right here, this guy, is our average speed. So one of the most important things that we're going to talk about in calculus is a limit. It's really important that you understand this. So in order to make it super clear to you, what we're going to do is give you a mathematical definition, because nothing says common sense like a good mathematical definition. So we're going to assume f is defined in the neighborhood of c, and let c and l be real numbers. The function of f has limit L as x approaches c. If given any positive number epsilon, there's a positive number delta, such that for all x, 0 is less than the absolute value of x minus c, which is less than delta, which implies that f of x minus L, the absolute value of that, is less than epsilon, or the limit as x approaches c of f of x is L. Wow. What? Basically what we're talking about here is as you approach a specific number x on your function, as this x value approaches a specific number, where in the world are the y values approaching on your function? As your x coordinate approaches a specific number, okay, a specific place, a specific item, a specific thing, what value is your y coordinate approaching? And it's really easy to find that out. You can type a function into your calculator. You can go to that specific value of x that you're interested in and find a matching y value. It's that simple. Sometimes it doesn't quite happen quite that pretty, and we're going to look at some different examples of that. But we just want to know, with all of this limit stuff, as x approaches a specific place, what value is your y coordinate approaching? Okay, on this page right here, we've got a ton of different properties for limits. And you're going to use these all the time. You might not even realize you're using these properties, but you're using these properties, okay? So just take a minute real quick and pause the video and just write down what these properties look like. And I know some of it's going to look like really, really weird. That's okay. It's going to become normal later. Right now, brand new, totally crazy stuff. But as we start using limits more and more often and looking at the really neat things that we can do with these limits, then you're going to start using all these different properties. And you won't even realize it. You won't even think about division or multiplication or addition. You'll just break it down and you'll look at that whole limit and see what it's doing. So pause the video right now, get all these down, and when you're ready, start it up again or go to the next video, and we'll see how they're used. So to sum up the previous two videos now, or the previous two concepts that we've talked about with the definition of a limit and all these different properties, then what we've got is just kind of an example here of the limit as x approaches c of x cubed plus 4x squared minus 3. You know, we want to use some properties of limits to rewrite that equation. So basically, we're looking at addition and subtraction here. So we're just going to look at it as the limit as x approaches c of x cubed plus the limit as x approaches c of 4x squared plus the limit as x approaches c of 3. And this is not a plus, it's a minus. Wow, that was a big erase. So I'll redraw my limit here and my squared here. And so what does this look like for like a final answer? It's going to look like this. As x approaches c, c is some specific number that we are not exactly 100% sure what it is, except that it will be represented by c. So we want to know what happens when we get close to that. We substitute that value in for x, and when we substitute that value in for x, we end up with c cubed plus 4c squared. Just substitute the value in for x minus 3. There is no x value here. There's no x value here to substitute c into. But what about a different problem? That's just adding and subtracting, you might say. What about if I have division? It's the exact same steps. So we're going to look at the limit as x approaches c of the same type of stuff. So we can just go, you know, x to the fourth, which would be, let's just look at it this way. X to the fourth plus x squared minus 1 divided by the limit of x approaching c. Wow. The limit, there it goes again, as x approaches c of x squared plus 5. So how is this guy going to look? Well, we just substitute c in everywhere where there was an x, and we're off and running without a problem at all. So this is going to end up being the limit, the answer will be, as x approaches c, will be c to the fourth, because everywhere we see an x, we can put a c in its place, plus c squared minus 1. And then on the bottom is c squared plus 5. So that's the limit for these two things. Don't let these be horribly challenging and painful. And if you'll notice, on the second example in blue, we did everything we did on the first example in green. We just didn't write it out that way. And so we're using those properties without even thinking about it. So those things that we just did, where we took the c's and replaced them in for the x's on our limits, hey, guess what? That's a real life thing. Like, we can do that no matter what c is. And so if you've got some nasty, long, ugly polynomial function with all kinds of stuff going on, and we're looking at the limit of that function, like the limit of f of x as x approaches c, what we are super interested in, what really matters, what's really, really important, is what's going on at c, right there, at c. And so if we can figure out exactly what our value of our polynomial is at that point, we have the limit. Like, we have this. So we just want to look, and everywhere there's an x, we want to put in that x value we're interested in. Now, if you're dividing your polynomials, like in part 2 down here, if you're doing some division, we do have one little rule, and it's a rule that we learned in like 4th grade, and that is this, that no matter what happens, we cannot have a 0 in the denominator. So if we're going to end up with a 0 in the denominator, we don't have a limit. But if we get 1 or a fraction or some small number or a negative number or whatever, we're good. We just can't have a 0. Okay? And so this guy basically sums up the previous 3 examples. So if you watch those videos or watch this one long one, this sums up those previous parts. And then just wait, because what we're going to do next is see it in action. So, what does it look like in super duper real life for reals? Well, here we go. We've got some great examples to look at here. Let's just take this first guy. We've got a polynomial function, and we're looking at when x approaches 3. That means anywhere we see x, we put a 3 in for that x. So my problem becomes 3 squared times 2 minus 3. Now, this we can do. This is not hard math here. 3 squared is 9. 2 minus 3 is negative 1. So the limit, as we do all of this, is going to be negative 9. Okay? And we can do that on all of these guys. So what about part example as x approaches 2? Well, let's look at the next guy. We'll do them in red. So what we're going to do is we're going to look at 2, because everywhere we see an x, we're going to put a 2 in, squared plus 2 times 2 plus 4. All of that over 2 plus 2. And when you work all of this out, you're going to end up with, on top, 4 plus 4 plus 4 over 4. And so what is that going to be? 12 over 4, which is 3. Okay? Again, don't let that be super hard. Don't let that be super hard. Now, what about the next guy? The limit as x approaches 0 of tan x over x. Well, now we got to go back to some trig. Remember that tangent x is the same thing as sine x over cosine x. And so what we can do is we can look at this problem as the limit as x approaches 0 of 1 over x times tangent x. Okay? And 1 over x times tangent x is the same thing as 1 over x times sine x That's a really nasty cosine. Let me clean that up just a little bit. Okay. Now we substitute in zeros at every chance that we get. And so when we look at this, we go 1 over 0 times sine 0 over cosine 0. But wait, we have a problem. Not theta 0. The problem is this. The problem is we have 1 divided by 0. So if you'll notice, this guy right here throws this whole problem out of whack. So what we're going to do is we're going to erase this part and we're going to rewrite it in a little bit different way. We're going to say that this represents sine x over x times 1 over cosine x. Now, one of the things that I'm going to tell you that you're going to take on faith at this point in time is that the limit as x approaches 0 of this, okay? The limit as x approaches 0 of sine x over x is 1. So what I've got is 1 times 1 over 1. And so this guy actually equals 1. Now this is a tricky problem, so pay attention or not pay attention or rewind and watch again or ask or Google this question because it's just a little bit different. Okay. On the last question, what we can do is we can factor out the top. Now you may not remember this, but it factors as x minus 1 times x squared plus x plus 1. And then on the bottom it factors to x minus 2. So what we want to do is look and see, is there a way that we can put a 2 into the bottom? Because if you'll notice right off the bat, if I put a 2 in down here, I get 0. And we cannot have a 0 in the denominator. So do this. I'll graph it right now, and while I'm graphing it, you check it out. Okay? And you'll notice on my graph that as we get close to 2, something really interesting happens. The graph appears to have a vertical asymptote, and on the right side it's going up, and on the left side it's going down. So in this case, our limit does not exist. So we would just say does not exist. Or we would say D in E. Okay, so here's like real life applications of using all the different properties of limits. Don't let this be super challenging. It's not. Just substitute in whatever value you're approaching. Okay? Alright, so to go along with all of these limits and things like that, what we've looked at so far is what happens when a graph approaches a specific y value from both sides. In other words, if we were to just real quickly before we dive into this example say the limit, whoops, here we go. The limit as x approaches 2 of 3x. What we're really saying is what's going on when x is 2, and the answer to that is the y value is approaching 6. And we can see from both sides of the line, and if we look at this, if we just graph this line, we're going to have some line. It's going to look like about like this. And when we look at 2, right here 2, we're going to have a y value of 6. Well, that happens on both sides of this y value, okay? So it doesn't matter what side I'm coming from, I get to that y value. But one of the things that can happen is you can have a y value approach a specific y value from the left and then another y value from the right. And so that's what this example talks about. And that's what this rule is for one and two-sided limits. So a function has a limit as it approaches a specific number if and only if the right and left-hand limits exist and are equal. So back to this question that we drew up here really quick. When I come in from the left and I come in from the right, I approach the exact same number, okay? And for your notational purposes, this guy right here is from the right, and this guy right here is from the left, okay? So when you look at these examples that we've got down here, that I've put down here for you guys to check out, notice that on my step function, I've got these straight lines, and as I come into, say, 1.5 from the left or the right, I've got one number from the left, I've got another number from the right that I'm approaching. And so we would talk for this particular guy right here, we would talk about a left and a right hand limit. Okay? Sometimes piecewise functions are equally crazy. So if we call this like say 1, 2, 3, 4, 6, 7, 8. Okay. As we come into 1, there's nothing from the left. Like there's nothing from the left that we approach. But as we come in from the right, on the 1, we're approaching this guy right here. Let's just call him 1. Okay? So this would only have a right-handed limit. And in fact, if you look at all of these, the only on this piecewise function, the only one that isn't just a single-handed limit, just a coming in from just right or just left. The only one that isn't is this point right here. We've got a limit because we're approaching the same thing from the left. Let me get that little mark out of there. Approaching the same thing from the left as we are from the right. Now my marker won't work. What the heck? Here we go. So as we come in from this way, from the left, and we come in from the right, we hit one spot. Okay? But on all these other guys, this is only going to have a right-handed limit, only a left-handed limit, only a left-handed limit, only a right-handed limit, only a left-handed limit, and only a right-handed limit. And so none of these actually have a specific limit except that guy. Okay, so it's kind of a lot to take in, but check it out. If you have questions you need to ask, you can always tweet to at HazelCalc or Hazelwood Math, or you can hashtag HazelCalc, and we'll see those questions and answer those as best we can. All right, the last thing that we're going to talk about in this section is a pretty difficult concept to understand, and it's called the sandwich theorem. It's difficult to understand because it's difficult to think of the sandwich part, but it's actually easy to understand when you see how it works. For example, sometimes in calculus, and not a lot, but often enough, there are things that we cannot find directly. Okay, so sometimes we just can't find a limit directly. However, we can find a limit indirectly by using what's called the sandwich theorem. So if I can find 3 related functions where one is smaller than the next, which is smaller than the next, in this case f, h, and g, f, and h. So if I can find a set of functions so that g is smaller than f, which is smaller than h, okay, where x doesn't equal a specific value, okay, then what I'm looking for is a place where I can get a common limit between g and h, and since g and h are on the edges, if they go to a specific spot, then the middle guy has to also go to that specific spot, okay? So it's really kind of a difficult concept to think about it, but here's the best way to look at it. We're going to Subway. We're going to eat a Subway sandwich. And when you bite into a Subway sandwich, you bite through the bread first, on the top and on the bottom. And inside that Subway sandwich are all the fixins. That's the function we're interested in. The bread at Subway is good, but what makes a Subway sandwich really good is the inside. And the same thing with calculus. We're really interested in that inside part, the really cool part. So G and H become the bread. We don't need this guy. And the F is the sandwich part, the in the middle part. So here's how this would look kind of in real life. If we look at the limit as x approaches 0 of x squared times sine of 1 over x, you'll notice right off the bat that if I put a 0 in here for x, if I put a 0 in, hey, guess what? Then I'm going to get an undefined answer because you cannot have a 0 in the denominator. You just can't. So what we have to do is go, okay, I can't look at this directly, but what if I were to squeeze this entire function in between 2 others that were a little bit bigger? Now, think about what you know about the sign. The sign will never ever be larger than 1 or less than -1. Okay? So for this particular problem, what we can do is we can look at the x squared part. He's going to be what we can look at. So let's look at negative x squared for the g of x part. And let's look at positive x squared for the h part. Now, if you think about this, the largest that sign can be is 1 or negative 1. So times x squared, the most that would happen is an equality. Okay, we would have an equality with x squared. So in between these guys, we've got x squared times the sine of 1 over x. So this becomes my f of x part. Well, what do I do? This right here. We're going to look at the limit as x approaches 0. That part doesn't change. But now instead of looking at this purple equation here, we're going to look at negative x squared. And then over here, the limit as x approaches 0. And we're going to look at positive x squared. And so when we do this, what happens is we can substitute 0 in. So 0 squared is 0, and 0 squared is 0. So since both of these guys go to the exact same number, 0, then we can say that the limit of this, the limit as x approaches 0 of x squared times sine 1 over x is 0. And I'll give you a chance you could graph this on your own. And when you graph both of these functions, negative x squared and positive x squared, and x squared sine 1 over x, you'll see that the trig graph bounces back and forth between the two x squareds, therefore giving us that sandwich.